We are about ready to start section 8.5, the ratio test, and also the root test will be in this section. But first, let's make sure that we know what we have so far. The two most easily recognizable series are geometric series and p-series. For a geometric series, you've got terms in here that look like some constant times a ratio to the k minus 1 power. So in other words, it looks like a times r squared, a times r cubed, and so on. Sometimes you have to run out of first few terms or so that you can tell that you get from one term to the other by multiplying by a constant. And that constant is r. And our conclusion is that if r is smaller than 1, this series converges. If r is not, if r in absolute value is smaller than 1, because this is one of the few tests we have where r, or our terms in the series, can be negative. If the absolute value of r is bigger than 1, the series diverges. There's no such thing as a geometric series where r is equal to 1. That would be clearly a divergent series because the limit wouldn't go to 0. So an example of such a series would be 1 plus a half plus a fourth plus an eighth, and so on. Here, each term, get from one term to the other by multiplying by a half. So it's a geometric series. R is a half, which is smaller than 1, so it converges. And remember, this is one of the few series that we know what it converges to. It'll converge to a divided by 1 minus r. So in this example, it converges to a, which is our first term, 1, over 1 minus a half. This one converges to 2. For a p-series, p is the fixed number, and k, the counter, is the base, p is a power. So it looks something like 1 over k to the p. And we are able to determine what makes this thing converge or diverge by the integral test. And what we found out was that if we were going to integrate this as k to the minus p dk, we would get k to the minus p plus 1 over minus p plus 1. And in order for this to converge, we needed this term to go to 0. The only way that will happen is that if p were smaller than 1. In other words, if p were bigger than 1, in other words, the exponent was bigger than 0. Well, the exponent's always big. We need the exponent to be bigger than 1. So we need converges if minus p plus 1 is bigger than, I've just said all of this wrong, and that's because my cat just came into the room and threw up all over my bed. So let me try this again. All right. If you're to integrate this, k to the minus p, with respect to k, you get k to the minus p plus 1 over minus p plus 1. And we would need the limit, as k goes to infinity, of this thing to be finite. The only way that will happen is if this thing here, we need that to vanish. We need that in the denominator. So we need minus p plus 1 to be a negative number. That's going to be negative when minus p is less than minus 1, or when p is bigger than positive 1. So p-series converges only if this power is bigger than 1. So we have that a series that looks like 1 over k cubed is a convergent p-series. whereas the series 1 over k to the 1/3 is a divergent p-series. Right? Converges if p is bigger than 1. It diverges if p is less than or equal to 1. Telescoping series are somewhat harder to recognize unless you write out the first few terms. And then we can decide whether a telescoping series converges or diverges by looking at the sequence of partial sums. So an example of one of those would be something like the sum from k is equal to 1 to infinity, 1 over k minus 1 over k plus 1. If I write out the first terms, the first term looks like 1 over 1 minus 1 over 2. Now k is 2, I get 1 over 2 minus 1 over 3, 1 over 3 minus 1 over 4, and then you can see that this thing here telescopes. So if you look at the nth partial sum, Sn is going to have the first term 1, and the last term, well, this term way out here is going to look like 1 over n minus 1 over n plus 1, and this one's going to add out with the guy before him, so we'll just have 1 minus 1 over n plus 1 in this example. And then the limit as n goes to infinity of our Sn term here looks like it's going to be just the 1. And so our conclusion is when the sequence of partial sums converge, that implies that the series converges. Okay? Kind of tricky to recognize a telescoping series. You got to kind of sniff those out. If it's not geometric, it's not a p-series, and you can't quite tell if it's a telescoping series, then try a quick test for divergence. Remember, our test for divergence is that in your series, if you take the limit as k goes to infinity of the ak term, and it's not 0, then the series diverges. So for example, if I had a series that looked like k over k plus 1, then I can kind of quickly see, now especially since you've been warned, that the limit of that general term is going to be 1. That's not 0, and so you're done. Series diverges. If the limit is equal to 0, you got to go on and try something else. So one of the other things that you can try, if it's something you need to try a test on, can you integrate it? By now you should have some idea of what you know how to integrate. An example is maybe you want to test the series 1 over k times the natural log of k. Okay, I can integrate this. I can take f of x to be 1 over x ln x. I think this one we have to start k at 2 since the log of 1 is not defined. And then we have to say that f is positive, right? And from 2 to infinity it is positive. It is decreasing, since as x and log of x grow on the bottom, the fraction gets smaller and smaller, and that it is continuous. And then we look at the integral from 2 to infinity, 1 over x ln x, and the series does whatever the integral does. This integral, you take u to be the natural log of x, du is 1 over x dx, so we're just integrating 1 over u du. We'll get the natural log of u, but u is the natural log of x. We're taking this from 2 to infinity, and so you see when this is infinity, natural log of infinity goes to infinity, so the integral diverges. implies the series diverges. Okay. Comparison tests are things that look like geometric series but aren't quite geometric, look like p-series but aren't quite p-series, or have numerators and denominators that behave like polynomials. For example, if I wanted to run a comparison test on k squared plus 4 over k to the 6th plus 8k plus 2, then I can say, well, let's compare to the series k squared over k to the 6th, which is 1 over k to the 4th. This series that I'm comparing it to is a convergent p-series. I can do the direct comparison test or the limit comparison test. I'm going to do the limit comparison test, so I don't need to worry about the sign. Remember that in the limit comparison test, if the limit of the AK's over the BK's is a positive finite limit, then both do the same thing. So if I take my AK's here and divide it by my BK's here, so I'm doing the limit comparison test, k squared plus 4 over k to the 6th plus 8k plus 2 divided by that, which would mean multiply by the reciprocal, then both of these would be 6th degree polynomials. So this limit is going to be 1, right? When I multiply this one times that one, I get 1 times k to the 6th over k to the 6th. So my limit is 1. So I get a positive finite limit. That means they both do the same. Earlier I said I had a convergent p-series as my comparison series, so our series converges. I could have done a direct comparison test, but remember with the direct comparison test, we have the two size comparisons, that if our series is smaller than convergent, it's convergent, or bigger than divergent, it's divergent. And since I took away terms from both the numerator and the denominator when I made my BK, I didn't know how they compared in size. So the handy-dandy limit comparison test worked for me there. The Q-log series was something that came out of the zero infinity case of the comparison test. The Q-log looks something like k divided by the natural log of k raised to the q power. And it had the same requirement for convergence as the p-series. It's converges if q is bigger than 1, it diverges for q less than or equal to 1. Okay, those are kind of a mishmash of the tests that we have. We will do some more reviewing of the tests, but make sure you learn the statements of the tests. We're going to encounter some series that have terms in them that have factorials and powers that are k powers. And so some tests that work real well on those are the ratio test and the root test. So here's a reminder of what k factorial meant. K factorial means k times all the previous integer values lower than k. For example, 5 factorial is 5 times 4 times 3 times 2 times 1. So k factorial is k times k minus 1 times k minus 2 all the way down to 1. The ratio test and the root test operate on the premise that not only do we need our terms decreasing to 0, we need them decreasing to 0 fast enough. Just like in an integral test, we need the curve to seal off towards zero fast enough for the area to be finite. For the sum to be finite, we made our terms to decrease rapidly to zero. So we look at the next term, which is the AK plus 1, divided by the current term, AK. So the one on the right is divided by the one on the left. And then we look at what's happening to that ratio as k goes to infinity. Suppose that as k goes to infinity, you get some number L as a limit. The size of L is going to tell us whether this series is going to zero fast enough. If L is smaller than 1, that means the next term is going to be much smaller than the previous term. So our limit's smaller than 1, and the series converges. If L is bigger than 1, then my next term is a little bit bigger than my previous term, which means it's not going to zero fast enough, and the series diverges. The only problem is if they're real close to each other and you get a limit of 1, then this test fails, and you have to try something else. But like I said, if you've got k factorials and k powers, it works real well. And I was going to show you that it works real well on a series that we know and love. Remember, this is a p series, 1 over k. P is equal to 1. This was the p series that was the harmonic series. We can show easily with an integral test that it diverges, but it's a p series where p is 1 and we know it diverges. But let's do the ratio test on it. We take the limit as k goes to infinity of the k plus first term over the current term. Simplify that. And I get k over k plus 1. So that limit we can take by looking at the ratio of the coefficients, and look, we get 1. Even though this is such an obviously diverging series, this ratio test is inconclusive. Right? We need a limit to be something other than 1, bigger than 1 or smaller than 1. So you still have to pay attention that this is a p series where p is equal to 1 and it diverges. Okay? But if you look at the next example, I've got a k power and I've got a k factorial. Watch how nicely the ratio test works. So we're going to take the limit as k goes to infinity of the ak plus 1 over the ak term. To get the ak plus 1 term, we just increase each k, replace each k with k plus 1. So my k plus first term will have a 5k plus 1 here and a k plus 1 factorial here. Then we have to divide it by the term as we saw it, 5 to the k over k factorial. Okay, so we'll do the flip and multiply step. We'll have 5 to the k plus 1, which I'm going to write as 5 to the k times 5 to the 1 over k plus 1 factorial. Now I'm going to flip this over, so the k factorial is going to be up here, and a 5 to the k is here. That's why I wrote the 5 to the k plus 1 in this way, because I knew I was going to be able to cancel here. Now I'm going to think of k plus 1 factorial as k plus 1 times k minus 1 times k minus 2 all the way down to 1. But that'll be k plus 1 times k factorial. So I'm going to write that up here. Keep that as k factorial, but replace k plus 1 factorial with k plus 1 times k factorial. Now I can cancel, and I take the limit as k goes to infinity of what's left, 1 over, oh, I've got a 5 up here, so 5 over Oops, I canceled the factorial. Let's get rid of that. I got a 5 over k plus 1. And since this limit is 0, my conclusion is that the series converges. The exclamation point because I had factorials. All right, the next one. We're going to try the ratio test here. I've got factorials and powers of k. So here we go. Let's go with the ratio test. I'm going to form the limit. As k goes to infinity, ak plus 1 over ak. So k plus 1 factorial. Then down here I'll have 2 times 3 to the k plus 1. Then that's going to be divided by the series as we see it. K factorial 2 to the 3k. Come down here. We're going to flip and multiply. So I'm going to have k plus 1 factorial. Let's distribute through here, and we have 2 to the 3k plus 3. Then up here we're going to have 2 to the 3k over k factorial. So I'm going to put that extra step in here where I rewrite k plus 1 factorial as k plus 1 times k factorial. And I rewrite 2 to the 3k plus 3 as 2 to the 3k times 2 to the 3. So here's the k plus 1 times k factorial. Then I've got the 2 to the 3k from my flip and multiply step. Then I've got 2 to the 3k times 2 to the 3 times k factorial. And now let's cancel here and here. And so we are left with k plus 1 divided by 8. Since the k's on top, this limit's going to go to infinity. Well, that's pretty much bigger than 1, so the series diverges. Okay. I don't suppose we need example 4. That's going to work like example 1. So the idea here is that there are no factorials, no k powers. So the ratio test was going to give us a limit of 1. So here you have your choice of what test you want to use. Try the ratio test. You're going to see, just like in example 1, the test will be inconclusive. So when I look at this thing, I think, well, I know how to integrate it, and I also can compare it. So I can do a direct comparison, or I can do an integral test. Either one of those should work to show me that this series is going to diverge. Let's do a direct comparison test, because we haven't done one of those today. I'm going to compare to this guy, 2 times k. So I know that, maybe I can't do a direct comparison. 1 over 2 to the k, sorry, 1 over 2 to the k. I have that 2 to the k is bigger than 2 to the k minus 1. So 1 over 2 to the k is smaller than 2 to the k minus 1. I know that this is a divergent p-series because my power is a 1. And I know that terms in the series that I'm testing are bigger than a divergent series. So we have bigger than divergent is divergent. Our series diverges by the direct comparison test. But try it later on with the ratio test. You should see, because this has polynomial terms and no factorials, no k-powers, that the ratio test is not going to be conclusive. A special case of the ratio test is called the Caithe root test. And it works if every single term in your series has a k-power on it of some type. What the Caithe root test says, if you peel off that kth power by taking a kth root and take the limit of that as k goes to infinity with the same three conclusions as we had with the ratio test, then you can decide whether the series converges or diverges. If the limit of the kth root is smaller than 1, the series converges. If the limit of the kth root is bigger than 1, the series diverges. And if the limit is equal to 1, the test is inconclusive. So, in my first example, there's my k power right here. So I'm going to do the kth root test. I'm going to consider the limit as k goes to infinity of the kth root of 1 divided by the natural log of k to the k. The kth root of 1 is 1. The kth root of the natural log of k to the k is the natural log of k. This limit has a value of 0. If the limit is smaller than 1, the series converges. In the second example, I've got a k squared on everything as the power. So there's a power of k. Let's do the kth root test. Let's take the limit as k goes to infinity of the kth root of k plus 1 over k to the k squared. Do you know what the kth root of that quantity to the k squared is? A kth root is a 1 over k power, and when you raise a power to a power, you multiply exponents. So k squared times 1 over k leaves me a k here. Oh my, that looks like a complicated limit. Look at what happens. As k goes to infinity, inside the parentheses, k plus 1 over k goes to 1, and then the exponent goes to infinity. This has the form of 1 to the infinity power. Well, then you set that equal to L, take the natural log of both sides, right? We're going to bring the power down with our logarithm. I'm going to have the natural log of k plus 1 over k to the k is equal to the natural log of L. We use the logarithm so that we can bring this guy down in front. So we have the limit as k goes to infinity of k times the natural log of k plus 1 over k is equal to the natural log of L. Now as k goes to infinity, the first factor goes to infinity. The second factor becomes the natural log of 1. The natural log of 1 is 0. So this is an indeterminate form. Remember, we fix that by taking the polynomial term and putting it in the denominator as a 1 over k. And now it has the right form. I've got the natural log of 1, which is 0, and 1 over infinity is 0. I've got the right form to use Lhopitals Rule. Which says take the limit of the derivative of the top and divide it by the derivative of the bottom. So I'm going to need a new page, and so I'm going to take the derivative of the log of k plus 1 over k first. So it's 1 over k plus 1 over k. Now I take the derivative of k plus 1 over k with a little quotient rule action. So it's bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Then I'm taking the derivative of the bottom. The bottom term in that test was a 1 over k. The derivative of that is negative 1 over k squared. And all of that is equal to the natural log of L. So firstly, this thing simplifies to k over k plus 1. Inside here, I have a k minus k, minus 1. So I get a minus 1 over k plus 1 squared. Then I'm dividing by this. To divide by that, we'll flip it over and multiply. How about that for some algebra? Well, the minus ones cancel. On top, I'm going to get a k cubed. On the bottom, I'm going to get a k plus 1 cubed. But I'm going to get a third degree power on k on top, a third degree power on k on bottom, so this limit should just be the ratio of the coefficients. The ratio of the coefficients is 1. Now that's the natural log of the limit. E to the 1 is the limit. Well, how big is E? Bigger than 1 or smaller than 1? Well, E is 2.718-ish, which where I come from is bigger than 1. And remember, in this test, if your limit is bigger than 1, it means your subsequent terms are not getting smaller, and so the series is going to diverge. So there you have it, the ratio test and the Caithe root test. Good for things with factorials and k-powers. So have at it. I think you'll like the ratio test. I think that'll probably be your favorite, and you're going to try to use it on everything, but remember, it's not going to work unless you have factorials and k-powers. It'll fall into that inconclusive case. All right, this concludes section 8.5 lecture, and I see I've got a big old pile of cat vomit on my bed that I need